Howdy. Welcome back to the Bureau of Economic Geology's Austin Earth Science Zoomerama. Today's presentation is from a team of geoscientists with the Bureau's own Gulf Coast Carbon Capture Center. They will address several topics relating to climate change and its mitigation through carbon capture and storage in their presentation entitled CO2, Too Much of a Good Thing? Thank you for joining us.
Hey everyone, so thank you Linda for introducing us. So my name is Margaret. I am currently an undergraduate at UT studying geology, and I'm also minoring in computer science and women's studies just for fun. So I've been at the Carbon Center for about 2 years, and it's really helped me hone my interests. So when I first started at UT, I really didn't know what I wanted to do, and I've kind of been able to develop what I wanted to do through doing this research. So today I just want to talk to you about how greenhouse gases work in the atmosphere and kind of what they do. So yeah, how do greenhouse gases work in the atmosphere? So to start off, I want you to imagine two different situations. So first, imagine it's 25 degrees outside and you're driving in this convertible. Think about, do you think it'd be comfortable to sit in this car? And it might be obvious to you, the answer is probably not. So our second situation, it's 100 degrees outside. This is Texas, it's July, your car's been sitting out in the sun for maybe 2 hours. And again, think about, do you think it'd be comfortable to sit in this car? Probably not. So they might seem like obvious questions, but the car scenario really helps us understand what's going on in Earth's atmosphere. So here we have the Earth. You can see this thin layer of gases that goes around the Earth. It's composed of several things. Some you can see I have carbon dioxide, water, and methane. So the way this works is our rays from the sun, our light energy, will come down through the atmosphere and hit Earth. And then it will transform into heat energy and bounce back up to this layer of gas, this atmosphere. And when it hits those greenhouse gases, some of this heat energy, you can see, comes back down to Earth, and some of it goes out into the atmosphere. So what happens if we have more greenhouse gases, more of that heat will end up staying inside that layer of gas, inside the atmosphere. So as we put more greenhouse gases, you can imagine our atmosphere getting thicker and thicker. And so it's very helpful because it can help protect Earth from the cold, dangerous space, like in our 25-degree car. But sometimes these greenhouse gases can be a little bit too much. So Austin will explain a little bit more about why this happens.
Hi, my name is Austin, and I'm going to be talking about how greenhouse gases work on a very small scale. So like Margaret, I'm an undergraduate majoring in geology, and I'm also majoring in chemistry, and I'm a member of the Longhorn Band and the organization Texas 4000 for Cancer here at UT. I've been working as an undergraduate research assistant at the Gulf Coast Carbon Center for about a year now, taking old scanned graphs from wells and digitizing them so that we can have the computer data and see which wells would be good candidates for carbon sequestration. So for the past 50 years or so, the term greenhouse gas has been becoming more and more common in the media, just as the gases themselves have been becoming more and more common in the atmosphere. So many people don't really know what the words greenhouse gases mean despite this, although you might think images of industrial smokestacks spitting black fog into the atmosphere. But as Margaret talked about, greenhouse gases do one thing. They let sunlight in through the atmosphere, but they prevent the heat that comes in with the sunlight from escaping. But how does this work? What about these gases makes it so that they trap heat in the atmosphere? There are several greenhouse gases, with the main ones being carbon dioxide, methane, nitrous oxide, ozone, chlorofluorocarbons, and water vapor. Carbon dioxide is the main gas that human activities emit, and it gets its name from its structure: 1 carbon atom and 2 oxygen atoms. Di equals 2, oxide equals oxygen. So what are some activities that you all can think of that produce CO2? If you thought of Combustion, then that's right. As you can see in the picture above, burning a fuel in a transportation vehicle is one of the most common ways of releasing carbon dioxide into the atmosphere. And so produce this. Every time you ride in a car powered by gas, you're really riding on a bunch of small, rapid combustions. A greenhouse gas like methane, however, may come from less glamorous places, typically from decomposition in places like wetlands or from fermentation inside of livestock animals. So that's right, a large part of methane emissions come from cow burps and farts floating up into the atmosphere. Gross. So all these gases have an important common feature. They're all made up of 3 or more atoms, while the 2 most abundant gases in our atmosphere, oxygen and nitrogen, have only 2 atoms. Because of these extra atoms, they have different ways in which they can move. So think if you have a rubber band and you're holding it between your thumb and index fingers and you're stretching it back and forth. No matter which direction you're stretching it, it's only moving in one direction. Now add a weight to the middle of this rubber band, something heavy enough to cause the rubber band to sag a little bit. And this is pulling it down and essentially adding an entirely new direction of motion, as you can see from the image in the top of the screen. This is essentially the effect of an extra atom in the greenhouse gases, and this added direction causes the gases to be more likely to interact with the heat energy that comes in with the sun. So think of a person walking down the street calmly with their arms by their side versus someone flailing their arms in every direction. Which person do you think is more likely statistically to bump into something? Typically, it's going to be the person flailing in every direction, as you can see from these pictures. The heat energy that the gases absorb is called infrared radiation, and it's the trapping of this energy high in the Earth's atmosphere that causes this change in climate on a molecular scale.
Hi, everyone. My name is John Freeney, and I work as a graduate student with the Gulf Coast Carbon Commission. This is my 2nd year as a graduate student and my 6th year in total being at the University of Texas. Currently, I'm working towards understanding what the coast of the Texas looked like about 20 million years ago. We as researchers kind of have a hunch that the Texas coast is a potential great place to store CO2. So we're trying to understand exactly what it looked like 20 million years ago and where we could put this carbon dioxide. Okay, so as Austin mentioned before, we have a couple ways that greenhouse gases, that they arrive in our atmosphere. One is being from cars that we drive around in every day. Second, as he mentioned, are from those cows, but not all of us are farmers. So we can think about a couple other ways that we produce CO2 every single day. For example, if you took a hot shower this morning, how did that water get hot? If you had breakfast this morning, did your gas stove, where did that gas come from? If you ever put on any makeup today, where do those products come from? So all these products have their basis in fossil fuels, and as a result, they all have CO2 that goes along with them. And this isn't a bad thing. Many of these products are necessary. It's things that we use every single day. But we just kind of need to understand where they come from and how much is too much. So looking at this chart here on the right, this shows the amount of CO2 emissions from different sources within the United States. And so looking at it, we can see the 2 major ones are transportation, just like Austin mentioned, driving cars, driving trucks, how do we transport all these goods across our large nation? And the second major category is electricity. So whether that be from heating our homes, electric stoves, hot water, how do we power this Zoom meeting that we're having? This is all coming from the burning of fossil fuels and the releasing of CO2. So how exactly do these energy sources release CO2? Well, first we can think about how humans breathe. So when each of us take a breath, we're inhaling oxygen. This oxygenates our blood, and at the end of it, we release CO2 when we exhale. Now, you can take that analogy and apply this to the combustion. Of course, there's no breathing going on, but we can kind of look at a candle to see it. So the candle is our energy source. It is combined with oxygen and then the flame. And the result is we have energy, which in the candle's case would be light, and CO2 and water vapor. So if you think about a power plant, that is just a really industrial sized version of this reaction happening. And instead of that energy being light like a candle, it's the energy that powers our homes, our computers, anything that requires electricity is coming from these reactions. So what you need to realize is that this isn't too much of a bad thing. If there's a balance in the world, so the CO2 that we're releasing from the power plants or from us breathing or from the cows that Austin mentioned, if those can be balanced out by natural sinks, that's okay. For example, plants in photosynthesis, they take in the CO2, they photosynthesize it, and they release oxygen. But the real problem is whenever this swings out of balance. So looking at the left here, we can see that it seems like the CO2 used by natural processes and the CO2 in the atmosphere is all balanced, all is well and good. But when this swings out of balance is whenever problems can arise. And we can see that really nicely on this next slide here. So this graph shows the last 400,000 years on Earth. And the line shows the amount of carbon dioxide in parts per million within the atmosphere. And going along, you can see that there's a nice cyclical curve. It never gets too high, it never gets too low. This is because the amount of CO2 in the air is balanced. We have a nice cycle going on. And then finally, at the very, very end of this graph, you can see that red line skyrocketing up. And that's from the result of human interaction pumping more CO2 in the air. And it seems like we're swinging out of balance. And that's something we need to worry about. And so that's why the work we're doing at the Gulf Coast Carbon Center is really important, because we're trying to mitigate these risks. And to learn a little bit more about how we can mitigate these risks, my friend Harry will talk to us about reduction of emissions.
All right, perfect. Thank you, John, for passing that off to me. My name is Harry Hull, and I'm a graduate student at the University of Texas, pursuing a master's in geology and a researcher at the Gulf Coast Carbon Center. I previously received an undergraduate degree in geophysics, also from the University of Texas in the Jackson School of Geosciences. And really, the reason that I chose UT at the end of the day was the ability to get involved in science from an early point in my career, and really pursue my passion for research, as is exemplified by my research currently working with the Gulf Coast Carbon Center. And so I'll share my screen, and what I'm going to talk to you guys today is about what we can do about CO2 and how we can reduce our emissions into the atmosphere. All right, so while CO2 emissions have the effect of warming our planet, the good news is that many engineers, scientists, politicians, and others have worked on finding solutions to this growing issue. Generally, there's two methods to address the carbon dioxide output into the atmosphere. And so the first of these is going to be shown up in the upper corner of this slide, which is reducing our carbon footprint, which is the amount of CO2 that we're responsible for. And then the second of these ultimately is going to be capturing existing and created CO2. And so let's see. The first of these that I'm going to talk about is going to be reducing our CO2 emissions. And so a question that you guys can think about is, how can we as individuals in our daily lives reduce our carbon footprint from every aspect of our day. And so I'll give you guys some of the answers that I've been able to come up with. But of course, there's this isn't a conclusive list, and there's many more that you can think of yourself. And so of course, some of these are going to include walking or biking places, as opposed to driving a car, carpooling or using buses or public transportation when available, driving more efficient cars, turning off unnecessary lights, or using LED lights, which tend to use less energy. Also, using less heat or air conditioning when possible, reusing and recycling plastics, purchasing green products such as wool or wool clothing, as opposed to other synthetic fabrics, which often contain, are made from fossil fuels as well. And then, of course, it is 2020, so of course we can always use reusable masks as opposed to disposable masks. And then, of course, buying local products, which tends to remove fossil fuel usage from the supply chain. And then, of course, many other options as well. And then, that's kind of what we're able to do on the, as individuals within a society. But we also, as a society, can address our carbon footprint as well at the city, state, or even country or global level. And so, what we can do about this as a society is another question that's important to think about. And so, maybe on the bigger picture, some of the things that we can do to address this CO2 use are switching away from dirty fuels such as coal, planting trees to offset CO2 use, using alternative energy sources such as wind, solar, geothermal, and hydro. And, I, of course, just listed the basics. There's, many others that are being considered as well. that you could name here. And then so the second method for dealing with CO2 emissions or reducing CO2 emissions in the atmosphere dealt with what we can do with the already existing and already created CO2. And so that's a question that I would like for you guys to think about as well, and is also something that we study here at the Gulf Coast Carbon Center. And the answer to that question is carbon capture. And so ultimately, there's a lot of CO2 that we produce that is a necessary byproduct for just living our daily lives. As I've previously listed all the ways in which or John previously listed all the ways in which we use CO2 every day. And so ultimately, there is going to be some amount of CO2 that we output, and capturing it and storing it in the ground is going to be one thing that we often are able to do to really reduce the CO2 in our atmosphere. And so ultimately, another question is, okay, what if you capture it, where can you store it? How do you know where you can store it, permanently so that it never enters the atmosphere again? And, so that's another important question to address. And ultimately, this is a carbon storage. And what we do is we store it under the ground. And that's why geologists like myself are, really get involved in the world of climate science, because these geologic reservoirs and geologic sandstones that we store these in are going to ultimately be important in the process known as carbon sequestration. And with that, I'll pass it off to Miliana, who will talk more about carbon sequestration and carbon storage.
Thanks, Harry. So hi, everyone. My name is Miliana, and I'm a graduate student at QT studying energy and resources. I finished my undergraduate 4 years ago, majoring in geophysics, and after that, I spent most of my time on rigs in the middle of the sea working for a national oil company. And so during my time exploring the Earth resources, I figured out about carbon capture and storage technology. I also found out that many of the things I have learned and done during my study and career can be applied to put back the CO2 underground. So last year, I flew across the globe to Austin to start my master's and working at GCCC to find the best layers in the Earth to store CO2. So right now, I'm going to be continuing what Harry has shared to you before about carbon capture and storage. So yeah, what is carbon capture and storage? Well, as you might have known, there are so much amount of CO2 released from fossil fuels, especially in power plants that produce energy for our daily use, as John has explained earlier. So most of those emissions are currently emitted to the air and cause global warming and climate change, just like what Margaret and Austin has explained before. So meanwhile, in CCS, we channel those CO2 emissions into a pipeline that will send them back into the Earth. I guess you might be wondering, how can we store emissions underground? Isn't it going to be dangerous? So, sorry. Right now, I want you to take a look at this styrofoam cup, and I'm going to show you what's going to happen if we bring it deep into the ocean. So yeah, as you can see, they shrink because of the high pressure in the deep ocean. The same thing happens with CO2 as well. So if I blew up a balloon, the balloon would be filled with CO2 and it would be as big as my face, or as you can see in the slide, it would be as big as this probably. But actually deep inside the Earth, the pressure and the temperature are higher than here up on the surface, and those conditions will compress the CO2, as you can see over here. Therefore, the CO2 will need much less space deep inside the Earth than it is up on the Earth. So the CO2 that you blow into a balloon before that was as big as your face might only need as big as your thumb of space if it's being put underground. But how can we keep the CO2 staying in the underground? What if they escape back onto the surface? So here's where my fellow geoscientists and I step in. We're looking for the best Earth layer to store the CO2. But first of all, what do you think the kind of rock that can be filled with CO2? So yeah, here we need to find the layer that is composed with porous rock, as you can see on the right-hand side, so that the CO2 can fill the spaces, as you can see between these grains. And so the CO2 can fill the spaces, but to make sure that the CO2 won't escape back onto the surface, we also need to find the Earth layer that is composed of the other rocks, as you can see over here. The layer with porous rocks must be located beneath a layer that is composed of a very tight rocks like this that does not have pores at all, so that the CO2 won't escape, so that the CO2 cannot pass through the layer and move back onto the surface. So that's how CCS works. And now Margaret will be back with you to explain to you further about research and also what does CCC do to help reduce the CO2 emissions.
Hey again. So everybody already kind of heard from me, but yeah, I just want to talk a bit more about what the Carbon Center does and how you guys can all become scientists too. So just to tell you a little story, when I was in middle school, I really did not enjoy any of my science classes, and I swore that I would never pursue science and I would never want to study it after high school. But clearly that didn't happen. And I just want to tell you that science is really not as scary as sometimes people make it out to be. First, I want you guys all to think about these two questions. What is research and what is the scientific method? So anyone watching this recording may have heard about these in their classes. So research is the careful study and investigation for the purpose of discovering and explaining new knowledge. So this can really be about anything that you're interested in. It could be about flowers. It could be about whether the bees in one area are different than the bees in a different area. Really anything that you could study and explain is research. And what is the scientific method? The scientific method is a method of research in which you identify a problem and then you gather data and then you form some hypothesis about what you think that data means, and then you test it. So again, this could really be any kind of topic. It doesn't have to be some kind of lofty idea that is really obscure. So basically, that is what we do at the Gulf Coast Carbon Center. We do research and we use the scientific method. So this is our group. These people really study a lot of different things. Some people study more chemistry topics. Some people study where to put CO2, like Meliana was talking about. Some people talk about, they research fluid flow, so you can see how those like compressed CO2 moves underground. Really so many different topics. And yeah, really, I mean, none of us presenters are really that much older than anyone watching. So you guys should just remember that this is something that you should consider, and you can really do science in whatever way you want. But this is just what the Carbon Center has kind of chosen to do. So with that, I will move on. We have a short trivia game. So this will be posted on our website later today, but I'll just kind of give a preview of what is going on. So today's categories in our game are greenhouse gases, carbon in the air and carbon in the ground, and then carbon capture and storage. So on your own time or with your teacher, maybe with some of your friends, you can go ahead and look at all these questions. So I can just give a few samples. Some of the questions are, how is the atmosphere like a car window? What happens to the atoms in CO2 when the sun hits them? So you guys can go back and look at this on your own time, but I just want to know you guys to know that it's available to you. So thank you. I think that should be it.
Thank you. Thank you very much. You guys did a great job. I really love the way you took your time to explain the issues and the basic science. And this idea that you talked about, Margaret, as far as research and the scientific method, one thing that I'm very proud of the scientists at the Bureau and your group for is it's used not just to acquire knowledge, but you're applying it to solve problems. And if that excites you in something that you would want to do to make a difference in the world, think about geoscience. They're relevant topics, and this is something that you could do and contribute to, just like this group. So I really appreciate what you've done. Thank you very much. Applause to you all. Thank you very much. And with that, we'll say thank you and end this session. For those of you watching on YouTube, if you have a question you didn't have answered, leave a comment below and we'll do our best to get you an answer. Also, check the description on the video links for more information at our website. And don't miss our next talk with Tiffany Cottle on hurricanes and the Texas coast, live Thursday, October 29th at 10 a.m. Central Standard Time, and soon thereafter on YouTube. Thanks for watching. See you next time.